All right. Well, hello, everyone. This is not working as I had expected. Just 1 second here. Very odd. Okay, well, anyway. All right. Well, welcome to another and perhaps our final episode of my walkthrough of A New Kind of Science, the NKS book, heading for its 20th anniversary, which is this coming Saturday. I had gone through all 12 chapters of the book in the course of 12 weeks, but we hadn't quite finished. So last week, we did part 2 of chapter 12, Principle of Computational Equivalence, sort of in a sense, the crowning chapter of the book. And I didn't quite manage to finish going through chapter 12 last week. We had a little bit left over. I said I would look at that today, as well as looking at some of the ancillary notes and general material associated with the book. So let's go ahead and jump in here and look at the remaining part of chapter 12. So chapter 12 here, Principle of Computational Equivalence. We'd gone through questions about what the principle is, questions about its implications for things like free will, undecidability, and tractability. And we talked at length about its implications for mathematics and its foundations, its implications for intelligence in the universe, the question of once you believe in computational equivalence, the realization that you can't make this kind of bright line distinction between what is intelligent and what is merely computational, its implications for technology, for this idea of mining technology from the computational universe of possible programs. What we didn't go through was the seemingly very small, very last section, historical perspectives. And this is really kind of reflecting on, and the notes to this section are quite extensive, and reflecting on some of the sort of philosophical implications of the principle of computational equivalence. And the first thing to say is that I kind of say it at the beginning here. I suspect this is a rather pithy piece in the end. It would be most satisfying if science were to prove that we as humans are in some fundamental way special and above everything else in the universe. That's something that we like to think. But it is one of the big things that science has tended to show is that, in fact, that isn't the case. And that the history of science, as I comment here, its great advances have precisely come from identifying ways in which we are not special, because that's what allows science to make ever more general statements about the universe and the ways and the things in it. So it's I comment about the fact that and so the progression of science, maybe I should just, there's really just text in this section. So let me just say, in kind of the progression of science has been, 400 years ago, the Earth is not the center of the universe. A couple of hundred years ago, there's nothing special about the origin of our species, there's nothing special about the physics and chemistry and other constituents that we have as organisms, so to speak. But still, there has been the kind of suspicion that there is something special about us. And in a common assumption is that it's something to do with the sort of intelligence or complexity that we exhibit. But basically, the principle of computational equivalence says that isn't true. Now, I want to make a meta comment here, which is that the thinking about kind of the role of humans in the universe and ultimately in the Ruliad is something that I understood pretty well at some level in working on the New Kind of Science. But 20 years later, there's a kind of new level of understanding that I've gotten from the physics project and from studying the Ruliad and so on. And I'll talk about kind of how these things fit together in a few moments. But one question is, if we look at the sort of computational raw material for us as humans, is there something special about it? Or is it just like the rest of the universe? Well, what the principle of computational equivalence is saying is No, actually, we might have thought, oh, we've built up to this level of computational sophistication beyond what has ever been achieved in the universe before, but it's not true. What we have is just equivalent to what's achieved elsewhere in the universe, and from our approach to fundamental physics, we kind of realize that physics is computational all the way down. So it's not the case. There's no place to find something different in specialness from what we already have in physics and what we see in us humans, so to speak. So there's nothing there's no special tower that's been built in terms of sort of the computational sophistication that we have. So I talk about, I talk about here this kind of idea that there is stuff in the world that is complicated and stuff that isn't. I talk about the fact that in early human thinking, it's very common to encounter the idea of animism, that systems with complex behavior and nature must be driven by the same kind of essential spirit as humans. That's the kind of weather has a mind of its own kind of idea, I say, but for thousands of years, this has been seen as a naive and counter to progress in science. Yet now, essentially, this idea, viewed in computational terms through the discoveries in the NKS book, emerges as crucial. So it's, as I comment here, it's the computational equivalence of us as observers to the systems in nature that we observe that makes these systems seem to us so complex and unpredictable. So, say, while in the past it was often assumed that such complexity must somehow be special to systems in nature, what the principle of computational equivalence now shows is that, in fact, this kind of complexity is vastly more general. And it extends not just to things in nature, but to things with abstract systems like simple cellular automata and so on. And I comment in the book here that it's perhaps a little humbling to discover that we as humans are in effect computationally no more capable than cellular automata with very simple rules. But the principle of computational equivalence also implies that the same is ultimately true of our whole universe. So while science has often made it seem that we as humans are somehow insignificant compared to the universe, the principle of computational equivalence now shows that in a certain sense, we are at the same level as the universe. But the principle implies that what goes on inside us can ultimately achieve just the same level of computational sophistication as our whole universe. But while science has in the past shown that in many ways there's nothing special about us as humans, the very success of science has tended to give us the idea that with our intelligence, we're in some way above the universe. But the principle of computational equivalence implies that the computational sophistication of our intelligence should, in a sense, be shared by many parts of our universe. It's an idea, I say in the book, that perhaps seems more familiar from religion than science, that our intelligence is, in a sense, shared by many parts of the universe. So particularly with all the successes of science, I say there's been quite a desire to capture the essence of the human condition in abstract scientific terms. And this has become all the more relevant as its replication with technology begins to seem realistic. That's what I wrote 20 years ago. The whole obsession with AI and AI ethics and all these kinds of things makes it all the more relevant as we think about replicating kind of the human condition in AIs. It becomes all the more important to sort of understand in scientific terms what this human condition really is. But I say what the principle of computational equivalence suggests is that abstract descriptions will never ultimately distinguish us from all sorts of other systems in nature and elsewhere. And what this means is that, in a sense, there can be no abstract basic science of the human condition, only something that involves all sorts of specific details of humans and their history. So in other words, it's if you say, what's abstractly special about a brain as compared to a rock, you might have said, well, a brain is computationally much more sophisticated than a rock. But actually, what you realize from the principle of computational equivalence is that, yes, we can identify in a brain all those neurons doing all those kinds of things, but in a rock, also, there are computationally sophisticated things going on of electrons moving around in all sorts of different ways. And the principle of computational equivalence says if we are sort of segmenting these things by their computational sophistication, we will never conclude that there's something fundamentally different between brains and rocks. So we've succeeded in scientifically kind of telescoping all of these different kinds of systems through the kind of lens of computation, of telescoping them all together, that there isn't this distinction between sort of the intelligent, the brain-like, and the merely computational. They're all in the same bucket. But as I already say in the NKS book, there's, as I say, there's, in a sense, can be no abstract basic science of the human condition, only something that involves all sorts of specific details of humans and their history. So as I go on saying in the NKS book, while we might have imagined that science would eventually show us how to rise above all our human details, what we now see is that, in fact, these details are, in effect, the only important thing about us. And that point is now echoed much more strongly in what I now understand about the Ruliad, and I now understand in terms of the way in which our existence defines a particular foliation, a particular position, a particular slice of the Ruliad, and that's how we are experiencing the universe and so on. That it is that specialness that we have, that particular feature of this is the particular place we are in the Ruliad, that's the thing that determines how we experience the universe and so on. And that the Ruliad in general is this whole story of computational equivalence and so on, but the particulars of us, that there's this, we can no more have a theory of the human condition in that sense than we can have a theory of why we are at this place in the universe rather than at some other place in the universe, in physical space. It's the analogous question in Rulial space is essentially just this question, why the human condition and not something different? So, okay, in the NKS book, I go on and say, and indeed, it is at some level the principle of computational equivalence that allows these human details to be significant. But this is what leads to the phenomenon of computational irreducibility, and this is in turn what allows history to be significant, and what implies that something irreducible can be achieved by the evolution of a system. So this is a point that's very relevant to the whole question of free will and so on. If there wasn't computational irreducibility, if you could always say, given a computation, there's always a way to have kind of an outside the computation view and to jump ahead and see what the answer is. You would say, we lead our lives, the universe does what it does, and we can jump ahead and say the answer is 42. And we don't have to go through that actual process, that actual progression of time to actually experience those things that happen. So in a sense, the leading of life, the progression of time, the fact that that is significant, the fact that that doesn't just telescope down to, and the answer is X, is a consequence of computational irreducibility. And the fact that computational irreducibility is a thing is a consequence of the principle of computational equivalence. Because if it wasn't for the principle of computational equivalence, one would say there's the super being that can, oh yes, there are lots of super beings and they can always see what the outcome of computations will be. The principle of computational equivalence says there are no super beings. We're all in it together, so to speak. Everything can experience this computation in a sense in the same way. Everything is computationally equivalent. And that's so this point about you can't jump ahead, everything in the universe satisfies this principle of computational equivalence. In fact, everything in the Ruliad, everything in the universe, of all possible experiences of the universe, so to speak, satisfies this principle of computational equivalence. As I mentioned in earlier sections here, there is what we would now call the hyper-Ruliad. There is the possibility of having computations which sort of just cache the answers to infinite computations in ordinary computations, but that's in the view that we now have, that's the domain of the hyper-Ruliad, and we are in the Ruliad and not the hyper-Ruliad, and there is an event horizon that separates the Ruliad from the hyper-Ruliad. So it's like saying, well, the hyper-Ruliad could be there, but we will never know it. The hyper-Ruliad, the existence of the hyper-Ruliad is something that is never knowable to us, and it can never affect us. And so we can have a sort of a conceptual debate about, is the hyperrulliad a thing, but it's never going to be relevant to our universe. In our universe, it is a contingent fact that we are in the rulliad and not in the hyperrulliad. And that's basically saying the principle of computational equivalence is true for our universe. And we now have vastly better evidence of that from the physics project than we had before. It seemed very likely before. It seems really, really likely now, as we can start to see down into sort of the lowest levels of fundamental physics in this computational kind of way. Okay, so I go on and I talk about, in the NKS book, I'm talking about the fact that computational irreducibility which is a consequence of the principle of computational equivalence, is what allows history to be significant and what allows time to be meaningful. That is, the progress of time to really be achieving something, as opposed to it's just a dial you turn. And what I've said more recently, as we've started to look at this multi-computational paradigm, which is kind of a story beyond the NKS book. I mean, it was hinted at in the NKS book, but was not taken seriously until very recently. The progression that I've seen is in kind of the way that we think about models in science. Is in antiquity, there were these kind of structural models, just the world is made of this or that. Then in the 1600s, with the arrival of mathematical science and things like calculus, we got to the point where there is a view of time. It isn't just what things are made of, but there's a view of dynamics, of progression in time, but it isn't really progression in time. It's just you can set the value of the time. Time is a parameter in the equations, and you can say, I'm going to run this slider, and I'm going to put the slider wherever I want, and time is equal to this. Time is equal to 1,000,000 years. What is the state of the solar system at that time, so to speak? So that's the view of time from the 1600s. The big new thing in the view of time from the 1980s, and from my idea of computational irreducibility and so on, then much more developed in the NKS book with the principle of computational equivalence, is this view of time in which time is the measure of the inexorable progress of computation. And time is not just a slider where you can move it wherever you want. Time is something that you have to progress through, that there really is a progress of time, that there are progressive steps in time rather than just time as a parameter and you can jump to any value you want. So in any case, I go on in this last section of the NKS book. I say, looking at the progress of science over the course of history, one might assume that it would only be a matter of time before everything would somehow be predicted by science. But the principle of computational equivalence and the phenomenon of computational irreducibility now shows this will never happen. So this is a very important statement, because it's basically saying one might have assumed, based on what one saw in the progression from the 1600s to today, that science would it'll solve it. Prediction is coming to everything. Everything will be predictable. You can predict the pandemic. You can predict the stock market. You can predict this. You can predict the motion. You can predict all these kinds of things. Everything will be predictable. And that is what science will deliver, is everything being predictable. But it's a crucial philosophical and conceptual point that I think is slowly beginning to seep into general awareness. But it is, in a sense, one of the most important conclusions, I suppose, for general philosophy of the NKS book, is science has limitations. And those limitations are eating science from the inside. It's not like one's coming and saying, oh, actually, there's this thing, it's theology, or it's something super science from outside of science. And you got to pay attention to that. It's coming from outside of science. No, this is something from inside science itself. It is science eating itself from the inside. It is this idea of the principle of computational equivalence, computational irreducibility. These are things that emerge from within the canon of science itself and show the limitations of science. Now, in a sense, there was a long prodrome to this from Gödel's theorem and things like that. But the interpretation, the kind of knitting that together with what that means for science, that's one of the big contributions of the NKS book, I think. And so this idea that the principle of computational equivalence says computation is everywhere, and the sophistication of computation is equivalent between all these different systems. That wasn't obviously the case. It could have been the case that there are these things like brains, like sophisticated computers that have a lot of computational sophistication, but most systems in nature don't have that. And that therefore brains and computers could outrun those systems in nature. And when the system in nature took all this effort to figure out what to do, we could just be super creatures and go and jump ahead and say, this is what's going to happen. And that science would achieve that. Science would achieve that predictability by being able to jump ahead, by being able to be more sophisticated than the systems that it was trying to predict. But the principle of computational equivalence says that's not true. That's not going to happen. There is computational irreducibility in the world. There are things where science will not be able to tell one, this is a prediction. We can generally predict things. In fact, one of the things that philosophers of science had kind of viewed in the 20th century, had viewed as being kind of a hallmark of science was this notion of predictability. But what this is saying is that's a naive view of what science is. That's science in the epoch of the 1600s. That's the mathematical science view of science. It's not the computational view of science. And it is a view of science that is a narrow view of science. It is not the case that we would be in a situation where we just throw up our hands and say, we can say nothing about the world. No, quite to the contrary, we can have a detailed theory of the world, but this question of whether we can run ahead and say, and the theory predicts this, where we can say, and this system is going to do this. We don't have to actually go through the steps. We can just jump ahead. There's sort of an implication that was taken from science of the 1600s that one would always be able to do this jumping ahead, and that's just not true. And that's important when it comes to saying, will we be able to predict something which has societal significance or whatever else? Oh, science will do it. Well, no, it's not true. It's the computational irreducibility implies that won't always be the case. There are things where we won't be able to make this kind of quick, glib prediction about what's going to happen. You always have to live it to see what's going to happen. And as I say, that is in a sense a good thing, because if that wasn't the case, we would conclude that the progression of time in our lives is really not significant. We could always just jump ahead and say, and the answer is this. Okay, so I go on in the NKS book, and we got to the last two paragraphs here. I say there will always be details that can be reduced further and that will allow science to continue to show progress. And that's another important statement. I go on and say, but we now know that there are some fundamental boundaries to science and knowledge. But the first statement there will always be details that can be reduced further. In other words, in any computationally irreducible system, there will always be slices, there will always be paths of computational reducibility. That's very important, because that basically tells one there is an infinite frontier for science, mathematics, technology, and so on. Within a computationally irreducible system, there will always be cheats, be jump aheads, be kind of ways to locally get ahead. You won't be able to globally say, and this is everything that will happen, but you will be able to locally get ahead. What does that mean? That means that you shouldn't give up on doing prediction-based science. No, you'll always be able to pick away at these predictions, this prediction, that prediction, the other one. But it's saying that there will be a fundamental limitation on global knowledge. You won't be able to say, and we nailed the whole thing, we got it all. But you will always be able to infinitely be able to pick away at particulars. And why is that important? For example, for technology, that basically says there's an infinite amount of technology to invent. We'll never run out of inventions. Within our universe, which is full of computational irreducibility, there will always be these little jumps of reducibility. There will always be this clever thing we can figure out, this clever invention that allows us to mine a little bit more of what the universe does in a way that is predictable to us. So that's it's rather pithily said in a couple of sentences there, but there will always be details that can be reduced further and that will allow science to continue to show progress, and technology as well, by the way. But we now know that there are some fundamental boundaries to science and knowledge. So then we come to the very last paragraph of the book, so I'll just read it because I think it's pretty pithy. And indeed, in the end, the principle of computational equivalence encapsulates both the ultimate power and the ultimate weakness of science. For it implies that all the wonders of our universe can in effect be captured by simple rules, yet it shows that there can be no way to know all the consequences of these rules, except in effect just to watch and see how they unfold. So what it's saying is, the principle of computational equivalence is both telling us that, yes, our level of computational sophistication, the one that is embodied in us humans, that's the same as the level for the whole universe. We have it. We know, we can have a conception of the computational processes of the whole universe. It's not the case that there's humans and then there's much bigger, there's the universe, and it's got a level of computational sophistication way beyond us humans. That's what people in physics, for example, had thought. Probably until pretty recently, actually, certainly in the 1980s, that's what they thought, that that kind of physics was something that fundamentally wasn't like a Turing machine, it wasn't computational, and that's something that now with our physics project, we can start to see it really is true. Physics is computational all the way down. So but the principle of computational equivalence already tells us it is a principle. It is it's sort of a bold principle that went out and said at the time of the NKS book, this is how the world works. The principle of computational equivalence is true. And that means that one of its implications is there's nothing about the universe that is computationally beyond us. So it encapsulates, as I say here, both the ultimate power and the ultimate weakness of science. The ultimate power of science in the sense that there is a thing, computation, embodied in the principle of computational equivalence, that is our way of describing the universe. We can successfully describe the whole universe. There is not a mystical force in the universe that is beyond what we can describe with this kind of computational methodology. On the other hand, it also encapsulates the ultimate weakness of science, because it tells us, while we can in principle break the universe down into this kind of computational components, we can't say based on that. You might have said, oh, we know what the components of the universe are. Great, we solved it, we have it, we know everything about the universe. Not true, because of computational irreducibility, because we need then to have this idea that that we have to kind of live through time. We have to actually see the computational progress of things. We can't jump ahead and just say, and the answer is this. So that's the sense in which it encapsulates the ultimate weakness of science, because if we believe in science as being the thing that allows us to get beyond what's happening in nature, this tells us that we won't in general be able to do that. So this last sentence, it implies that all the wonders of our universe can in effect be captured by simple rules. In other words, that it isn't the case that you have to invent. It's saying principle of computational equivalence is saying that computationally, the whole universe is equivalent to something that has simple rules. Yet it shows us that there can be no way to know all the consequences of these rules, except in effect just to watch and see how they unfold, which is kind of a statement of the leading of kind of the actual behavior of the universe, the actual leading of life is the way that you find out the consequences of it. So that's kind of that was the end of the book. And I just it's kind of interesting to compare the very beginning of the book and the very end of the book. The very beginning of the book, it begins by saying, the very beginning of the first chapter, 3 centuries ago, science was transformed by the dramatic new idea that rules based on mathematical equations could be used to describe the natural world. My purpose in this book is to initiate another such transformation and to introduce a new kind of science that is based on the much more general types of rules that can be embodied in simple computer programs. So we go from there, from this kind of the launching point is there is this way of describing the world that is computational, and that is kind of a step beyond what was introduced in the 1600s of describing the world mathematically. We go from there to this sort of final conclusion about the fact that when we describe the world computationally, we have this very these very deep principles of the principle of computational equivalence. We have these sort of deep philosophical consequences for our description of the world and for the role of science in the world. You know, I have to say that this to me was the sort of philosophical conclusion of the NKS book. Now, since that time, the whole realization of multi-computation, the whole idea that sort of really highlights this notion of not just the particular computation, but all possible computations and the entangling of all those computations and the role of us as humans being able to sample that. This is really built on the ideas in NKS, but it takes another step. And the very important step that came out from this idea of multi-computation is the fact that there is a generic kind of computational reducibility that exists in the multi-computational world for observers of the multi-computational world that are like us. So, in other words, there is all this computational irreducibility. That's crucial to all of the theories of physics that we have, all these other things that is kind of the paradigm we're now working on, the multi-computational paradigm that we're working on, this idea there's computational irreducibility underneath. But there's another piece, which is that the slices of this multi-computational world that we humans take have certain special attributes that cause them to have reducibility. And those special attributes are that we are computationally bounded, while the underlying processes of the world are computationally irreducible and involve all of this computational sophistication being employed. We, as observers of that world, are computationally bounded. We don't get to follow all the details of what happens to every atom of space, not even every molecule in the air. We don't get to follow those things. We only are sensitive to computationally bounded aspects of the way that the world works. So that's our first sort of way in which we're defining how it is that we sample the world. And the second thing is that we believe we are persistent through time. We believe that we have a single thread of experience and that thread of experience persists through time. Those two attributes, and this is one of the big conclusions of the physics project, those two attributes are sufficient to show us that general relativity and quantum mechanics must be true. In fact, that same attribute is what leads to statistical mechanics as well. The fact that the second law of thermodynamics is true, I've talked about this several times, is a consequence of the fact that we don't get to follow the motions of every molecule. We are looking in this aggregated way because we are computationally bounded observers. So in a sense, what we're doing is we're saying it's all principle of computational equivalence all the way down, but there's something special about the way that we are, the slice that we are taking of the world. And the specialness is because of these limitations that we have, computational boundedness and the belief of persistence in time. And those pieces of specialness imply generic features of the physics of our world. And by the way, also what we now realize, I talked about this before, it also implies things about how we observe the mathematical world and this meta-mathematical observer concept and so on. But that's sort of an extension beyond what I was doing in NKS. In NKS, we get to the point of saying there is this computational irreducibility. In the multi-computational paradigm, what we're now realizing is, and there is a special feature of how we humans sample that computational irreducibility, which allows us, which is sort of a statement of how science manages to get its handhold in this world of computational irreducibility. The answer is for observers like us, for scientists in a sense like us, there is this particular way that we're sampling things, which very immediately leads to these things which are core to the science that we experience. If we were aliens with different characteristics, with different ways to sample the Rulliad, the core of our science would be different. But what the NKS book does is basically to say there is this limitation to science that's associated with computational irreducibility. What we're now realizing with this sort of multi-computational idea is there are generic things that science can say, which we already knew that science could say, but now we know why it can say them, that are associated with our limitations as humans. All right, so one of the things about this last section of chapter 12 is that it's extensive in its notes. And let me look at the notes for this section. Actually, maybe there aren't so many, but they're pretty dense. So let's take a look at some of these notes. So I talk about human uniqueness. And I'm talking here about some aspects of sort of historical notes. Say the idea that there's something unique and special about humans has deep roots in the Judeo-Christian tradition. It's kind of the uniqueness of humans. It's not necessarily true. For example, in the Eastern religions, it is less true that there is this focus on the uniqueness of humans. They tend to view humans as one of many elements that make up the universe as a whole, as opposed to we're special, we're special. And as I comment here, even though that's a kind of deeply rooted tradition in Judeo-Christian traditions, there's sort of been a gradual dilution from science about the specialness of humans, but it's a very standard tenet of Western thought. So, okay, I talk a little bit here about animism. Remember, these are notes to this last section of chapter 12. Talk here about belief in animism remains strong in several hundred million indigenous peoples around the world. Not sure it's only indigenous peoples, actually. There are plenty of kind of sort of everyday sayings, from the weather has a mind of its own to other kinds of things, that are very much reflect an animistic view of the world. I comment here, animism not only involves explaining natural phenomena by analogy to human behavior, like, the Greek gods, it works this way because, Poseidon was angry at so-and-so, but also assuming that the gods can be influenced, so to speak. So in other words, if you put out the fruit bowl for Athena, then, Athena will favor your side in the battle, kind of thing. That's a kind of an extension of this view that the way the world works, the way nature works, is something that is sort of a mind-like thing, that we can give analogies to human behavior. That's taking that another step forward, that nature wants to eat the fruit bowl type thing. So this is something about history of studies of religion from the 1800s. This is sort of a common view of, I don't think I mentioned the Golden Bough, which was, I think, a later book about kind of the origin of sort of anthropological origin of religion. So there's animism, polytheism, when sort of there are, where you go from there is a god associated with that tree to a god associated with the concept of treeness or whatever. Comment here that in Roman times, I think it's true in many traditions, even today, that there's sort of this idea of gods associated with very particular concepts. The god of the software industry and things like this is kind of that type of concept. So then the big thing that came along was monotheism, that, roll them all together into one god type thing. There's a certain sense in which that has a resonance with the principle of computational equivalence, of roll together all those special purpose computations that happen in all these different venues into this one kind of global thing, the sort of the global idea of computation as a single concept, and ultimately leads to things like the Rulliad. I hadn't really thought about it that way before, but you can kind of think about, so, instead of the polytheistic, there's a god of every concept, there's this kind of, there's one god kind of idea. I talk here about Europe in the Middle Ages. There remained widespread belief in animistic kinds of explanations. Western superstitions center on animisms, as do lots of rituals in countries like Japan. Oh yeah, I'm commenting here, and I'm a little bit out of date, I suppose. Animism is also a key element of the New Age movement of the 1960s, as well as of ideas such as the Gaia hypothesis. And I kind of feel like, you know, be careful about the Earth type thing. There's a certain sense in which that's a return to a kind of a view of something sort of an animistic view, since you know, the concept of a religion where we identify a distinct kind of a distinct God is kind of in some places kind of in retreat. It's kind of, now we've got, you know, the Earth as our sort of we're back to this kind of spirit like belief system. Well, in any case, I can't comment on Jean Piaget, 1940s. Talking about children go through a phase of animism in which they interact with complex objects, much as if they were alive and human. I think that's kind of the anthropomorphizing of things. It's sort of interesting now as we do that with computers. Of you know, I've been thinking about what does it feel like to be a computer, so to speak, and you know, what does it feel like to be a fluttering piece of paper, and sort of the principle of computational equivalence, and this whole kind of everything is a bit. You know, everything has the same kind of computational equivalence, in a sense, mind-like quality, is that same type of idea. Okay, I'm going, let's go through a few of these others. The universe as intelligent. This is a thing that whether or not something like thinking can be attributed to the universe has long been discussed in philosophy and theology. So, I mean, again, these are slightly dense kinds of notes. So theism and standard Western religions generally attribute thinking to a person like God who governs the universe, but is separate from the universe. Deism emphasizes that God can govern the universe only according to natural laws, but whether or not this actually involves thinking to govern the universe that way, or whether it's just like the laws are set in place and now it's just the clockwork machine is running and no thinking God has to be there. I mean, I have to say that there's a certain resonance with the simulation argument in these kinds of views of God and so on. I talk here, pantheism generally identifies the universe and God. Its typical religious form in Eastern metaphysics, as well as in philosophical idealism, the contents of the universe are identified quite directly with the thoughts of God. Yes, I mean, well, I talk about scientific pantheism. The order of the universe is identified with God, so-called nature's God or Spinoza's God. I think it's kind of this nice thing that what happens in the universe is the thoughts of God actualized, so to speak. And that has a great resonance, I think, with my kind of view of the Ruliad and the necessary existence of the universe, in a sense that goes beyond kind of, it's the thoughts of God actualized, where there is a God making a choice about what the rules of the universe should be, to this idea that the Ruliad is a necessarily actualized thing because it is a pure formal abstraction. It is merely our particular place in the Ruliad that determines our experience of the universe and the universe as it seems to us, so to speak. So it's a little bit beyond this kind of thoughts of God actualized idea, because God still has a choice in that, from that point of view, whereas in the Ruliad there is no choice. I comment here whether that means in this kind of Spinoza's version of this, whether that means that there's thinking involved in the operation of the universe isn't clear. Oh boy, this is this was a note that I wrote because people regularly say, look, there's a lot that's in the NKS book that resonates with Eastern thinking of various kinds. You know, the challenge for that, I think I make comments here. Let's see. Similarity of human thinking to other processes may seem to fit with Buddhism. What I say about irreducibility of processes in nature to formal rules may fit with Taoism. But as I comment, like essentially all forms of science, what I do in the book is done in a rational tradition with a limited relation to the kind of traditions of Eastern thinking. And I think that's one of the challenges that in a sense is really made more evident by the discussion of the Ruliad and Rulial space and so on, is that we exist in a certain place in rulal space. We exist in a certain place in physical space. That is our way of thinking about things. That is our way of viewing the universe. Each individual one of us, in a sense, exists in a certain place in rulal space. We have a certain way of understanding the world. And as we go between people who've been, let's say, trained in the Western scientific tradition, and we go even to people with a different background, that distance in rulal space is not so small. And the translation of these are the concepts of kind of that come out of Western science, translate, or these are the concepts that come out of an Eastern tradition, for example, translating those concepts is not trivial. That is a distance in rulal space. It may be small to the distance to the extraterrestrial alien, so to speak, in rulal space, but it's still not totally small. And certainly for those of us who exist at our place in rulal space, it's like doing the translation, kind of getting those transportable concepts that are kind of like the particles of rulal space, transporting them to this place where we can be talking about this or that kind of non-Western tradition. That's very non-trivial. It's very difficult. I mean, I remember, I think when I was a kid, I was a little bit, I grew up in England, which is a country that I think since Henry VIII has had a national religion, so to speak. And so, there was always religious education in schools and so on. And so I did learn a bunch of interesting things that way, and even interesting philosophy and so on. But there was a certain, I remember there was a certain kind of strand that would find themselves on street corners and things of sort of the religious fundamentalist crowd, which one of the things that very much put me off that kind of tradition was, well, let me just talk to these people, let me discuss what they think. And there came this moment where they said, look, you are arguing that by logic, but we do not believe in logic. That is not our worldview. And I think that for many, many years, that was like, okay, I'm out of the game. That's a different game. I'm not able I'm not interested in participating in that game. But what I've increasingly realized is that this is kind of, it's a different place in rulal space. And one may decide, I like my place in rulal space, just like I like living in place X or Y. But it is not the case that one can, it's a different place in rulal space, and one can imagine a translation. One can imagine a view of the world that is different. It is very difficult to have a view of the world that isn't one's own view of the world. There may be views of the world in which one can make conclusions about things that are difficult to do from one's own view of the world, much easier from a different view of the world. We see that also in scientific paradigms. We have a view of the world, the sort of pre-NKS view of things like, complexity in nature and so on, very different from a post-NKS view. A scientific paradigm is the same kind of thing about it's a motion in rulal space. We are now managing to reach a different point in rulal space. We have this different paradigm that allows us to understand the world in a different way. That's kind of the concept there. And I think that's these different scientific paradigms are one kind of motion in rulal space. As we get to these different forms of thinking, that's a different kind of motion. And I don't think we have a good understanding. It's very hard to get, when you're not at the new paradigm or not at the different way of thinking, it's very easy to dismiss that different paradigm or that different way of thinking because just not the things you're thinking about. And often the kinds of questions that you can ask within your way of thinking or your paradigm are different from the questions that you can ask within that different way of thinking or that different paradigm. But that's kind of the challenge. And I would say that challenge is even clearer now with the Ruliad. How do we understand what it's like to be somewhere else in rulal space? And one thing I might say is that the NKS book, in a sense, is an example of rulal space travel in some sense. Because what it's doing is, with all its computer experiments and all its study of different systems in the computational universe, instead of saying, let us go from our understanding of things to another nearby understanding, it's saying, let's just jump out anywhere in the Ruliad. Let's just go look at how this particular rule that we pick at random in the Ruliad behaves. And that is, in a sense, it's sort of the the fact that we can do that, and that's a lot of what the NKS book is about, just go out in the Rulial spacecraft and just go zoom off into that direction that corresponds to register machines or something like this. Now, the thing that is true is that the big thing that pulls together all those different parts of the Ruliad, all those different places in Rulial space, is the principle of computational equivalence. That's the big principle that kind of tells us that there's something in common between all those different parts of Rulial space. So that's sort of the significance of that. Okay, there's more notes here to this section. I talk about aphorisms. You know, part of this and more of this has happened since the book came out is, and I'd love to collect more of these actually, it's a good project actually, is these aphorisms, like the pre-Socratics would say things like, you know, everything is full of gods. You know, well, we can take that aphorism and, you know, who knows what it meant originally, but maybe it meant something in a vague, intuitive direction that is similar to what we're now saying with the principle of computational equivalence. It's you know, it's sometimes, I think, reading blood out of a stone, so to speak, that you know, there's really just a stone there, and we're somehow reading that there's blood in the stone because that's what we're expecting or something, and it's a post hoc kind of thing, but it's still interesting as a way to kind of rattle one's thinking around, to look at these aphorisms and see how they play relative to one's current thinking. Okay, another note here on postmodernism. Boy, that's become has more taken over the world, I suppose, since the NKS book came out. But let's see. Gosh, this is even hard for me to read right now. Yeah, I mean, this kind of idea of everything, of relativism everywhere, so to speak. One of the things that comes out of the principle of computational equivalence is, well, that's not really true, because while there are these different, what we would now say there is these different places in the Ruliad, it's all one Ruliad. It's all one. The principle of computational equivalence is true everywhere. There is a fundamental ground truth that is common. Now, our view of it, the slices we take of it, may be quite different, but that doesn't mean there's nothing in common. It isn't the case that truth is a purely constructed separately for the observer, so to speak. There is a ground truth, but we see different parts of it, and it's very similar to the way that Plato would argue of things, I think. So I think the thing that has been added in more recent times by our thinking about multi-computation and so on is that for observers like us, there are great constraints on how we can view things. That is, you can imagine, you can say, well, if I wasn't an observer like me, I could view the universe this way, and I could have a completely different view of what's true, in a sense. But we are observers like us, and in a sense, that's part of the tension, I suppose, in some of the sort of postmodernism versus various kinds of traditionalism about views of humans and the place of humans in the world and so on, that there is a sense in which you can say, well, we could not be ourselves, and then we could think about things in this way. But the fact is we are ourselves. And it is a gradual process, and this is the interesting sort of self-fulfilling piece of this. It is a gradual process to become not ourselves, in the sense that as we build technology, we can, you know, at the beginning, we just have, you know, sight and sound and touch and so on. We have our ordinary senses. Then we build technology. We can measure all kinds of different things. We build technology. It allows us to sort of sample the world in different ways. As we have different kinds of ideas, it allows us to notice different things about the world. So in a sense, we are creating this different reality for who we are, so to speak, through things like technology and so on. But the fact is that for us intrinsically to just say, oh no, you know, let's just say we're not, you know, we could think of ourselves differently. Let's put ourselves in a place where sort of truth is different kind of thing. That's not us, so to speak. That's not the ordinary us. We can say, let's invent a version of ourselves in which we are that way, but that's not us. And so I think that's sort of the tension between kind of the postmodern, you know, let's deconstruct things and say it could be this way, but actually the way we are as humans, even the basics of, persistence in time and computational boundedness and things, even those things tell us certain global truths that will be true of any observer that is of that kind. Now, if we say, forget that, we're going to imagine that we're the aliens and that don't have those attributes, then indeed you can have a different truth, so to speak. The problem is that we aren't those things. We're not in that state. And while it is the case that we gradually evolve through technology and through different kinds of thinking, we gradually evolve to different places. We can't just jump and say we're there, because we're not. And that, I think, that understanding is sort of there's a tension created when people just say, oh, no, just jump to that place. So anyway, I think there's quite a bit more has developed in kind of the sort of the public view of these kinds of things since the NKS book. Another note, microcosm. The notion that the human mind might somehow be analogous to the whole universe was discussed by Plato and others, and known in the Middle Ages. But it was normally assumed that this was something fairly unique to the human mind, and nothing with the generality of the principle of computational equivalence was imagined. So I guess the notion that a mind might be the whole universe, because minds are really powerful things, is something that was thought about, but the notion that everything is a level playing field, that's kind of new to the principle of computational equivalence. Okay, this is a note that I've sort of embellished quite a bit in things that I've talked about in various kinds of futurism situations. Okay, so I comment the principle of computational equivalence and the results of the book at first suggest a rather bleak view of the endpoint of the development of technology. And I talk about basically the fact is that this is, I've referred to this sometimes as the box of a trillion souls, that basically there comes a time when we can emulate the principle of computational equivalence says it must be true, and we have increasing evidence over the last 20 years. It's become very clear that we can expect to emulate the processes of thinking in digital form. So we can imagine uploading a thing that is kind of like human thinking, like human experience, into this kind of purely digital environment, into this pure sort of computational thing. So you can have a trillion souls. The soul is the kind of engram of the human the computational engram of the human. There is the physicality of the human in terms of neurons and actual cells and things like that. But there is what a human stands for in some kind of more conceptual level. What in the past, in sort of the theological tradition, was referred to as the soul, we would now refer to as some sort of computational engram of the operation of the human. And in principle, we can imagine uploading that engram, that soul, to this box of a trillion souls, so to speak. And so then the question is, once you have the box of a trillion souls and you're holding it in your hand, it's got all of that stuff going on. You look at it and you say, somebody would say, that must be the most amazing thing in the universe, this box of a trillion souls. There must be something about it that is so obviously, luminously different from the rest of the universe. That will be an amazing thing, but it isn't true. Because the principle of computational equivalence says that box of a trillion souls, when you look at it in a sort of general abstract way, it's got all these particles and electrons and they're all doing these various things. You look at a rock and you see the same stuff. There is nothing abstractly different about that box of a trillion souls from the rock. So then the question is, what is the difference? And the difference is that the box of a trillion souls has the lineage of that whole, all of human history and so on in it. Whereas the rock is just a rock that has a lineage of geological history, but it's a different thing. And so in a sense, what that's saying is the specialness, this is an amazing rock. Yes, I'm sorry, this is an amazing box of a trillion souls as opposed to just the rock. It is amazing, but it's amazing because of the details of it, not because of something abstract, not because of some something where you can say from the outside, oh, I'm just going to make a statistical measurement and I can say it's amazing. Rather, it's the fact that it is the thing that is very special, very specific to our human history and so on. And that in a sense, the thing that is most special about us is our detailed specialness, so to speak, not something which is an abstract kind of specialness. It is not that the box of a trillion souls is abstractly more luminous or something than anything else in the universe. No, it's really very much the same as everything else in the universe. But what's special about it is the details of how it got there and the attributes of us, sort of the details of the human condition and so on, and human civilization that were eventually captured in that box. And so I think that now it's interesting to understand as you imagine living in the box, and you imagine, what are the human purposes? How did human purposes evolve? It's kind of the bad case of the kind of living in the box is, the future of humanity is a box of a trillion souls all playing video games for the rest of eternity. And to us today, that looks like a really crummy endpoint for the future of history. But the thing to realize is, that as we kind of go back and think about kind of the way in which we've gotten to where we are today, the way that human purposes have gradually evolved over time from, and many of the things that we're doing today are things that for which would be incomprehensible as human purposes even 1,000 years ago, where you'd have to explain this long chain of I'm doing this because I'm walking on the treadmill, because it will improve my health so that I will live longer, et cetera, et cetera, et cetera. Well, you might say, why? It's just like from a different points in history, the reasons for doing things are very different because there's a different stack of things that have developed in the civilization. And so similarly, it can very well be that the souls playing video games, so to speak, in this box have an absolute conviction that what's going on is purposeful within their notions of purpose that evolved by that time. And so it's an interesting question what the sort of evolution of human purpose looks like. I think one thing realized recently is this point that one of the things I have said after the NKS book is that imagine that we've got all these uploaded human souls, and what are they doing for the rest of eternity, so to speak? Well, they can live in an emulation of our actual universe, but maybe what they'll really do is to basically do NKS, do ruleology, explore the Ruliad. Don't just be in the universe as we experience the universe, experience the whole Ruliad. Go out and spend the rest of eternity exploring the infinite expanses of the Ruliad. Okay, so that sounds like kind of an interesting thing to do. It's a little bit of a kind of, you write the NKS book, and then pretty soon you say the future of everything in the world is everybody doing what's described in that book. So there's a certain, but the thing to realize is that there is a sense in which it's all sort of, it has a strange circularity to it, because in some sense, if we have a certain special slice of the Ruliad that is our existence, our experience, and so on. If we say, let's go out and just explore everywhere, let's delocalize ourselves to the point where we're no longer dealing with these specific places in Rulial space, we're just spread out throughout Rulial space. I think in most senses, we will then not exist, because our existence is a reflection of the specialness that we have as entities that believe we are persistent in time, et cetera, et cetera, et cetera. As soon as we say, let's actually go spread out and just sort of spread ourselves out throughout the Ruliad, that's the sense in which we will no longer exist, in the sense that we imagine existence today. All right, let's see. Oh boy. Okay, let me see. How many more things do I have here? That's the end. Okay, so the very last note in the NKS book is about philosophical implications, and I think there's a pretty dense note. And And I talk about the implications of the principle of computational equivalence for philosophy. Let me kind of mention a few of these things. So I mentioned that if we could only one area where the principle of computational equivalence has implications is in epistemology, the theory of knowledge. In the past, I say it's usually been assumed that if we could only build up in our minds an adequate model of the world, then we would immediately know whatever we want about the world. But the principle of computational equivalence through computational irreducibility means that we can't work out the consequences. And so there's this new limit to knowledge. There's this sort of boundary, this horizon of epistemology, so to speak. And I comment here that it needs a criterion more sophisticated than immediate predictability to assess a scientific theory. Right, so I'm talking about the sort of some things that have been very much informed by this meta-mathematics project that we've done recently. Let's see. I comment here, it's often assumed that one cannot learn much about the world just by studying purely formal systems, and that one has to rely on empirical input. But the principle of computational equivalence implies that at least at some level there are inevitably common features across both abstract and natural systems. So that's been very much more extended by the Rouliad and concepts around that. This idea of whether there is a need for empirical knowledge. The notion of empirical knowledge in the Rouliad is that the Rouliad is the Rouliad, and it is a necessary thing, and you can study it completely abstractly, and it can tell you about the world of all possible worlds. But the particularities of the world that we live in come from our particular experience of the Rouliad, and in a sense, that is a study, it's shining the light back on us. What are our attributes? And therefore, what is our slice of the Rouliad? What is our experience of the Rouliad there? So I talk about here in ontology, theory of being, principle of computational equivalence, often abbreviated PCE, implies that special components are vastly less necessary than might have been thought. Right, so I talk about here the need to, what are things made of? Well, the very fact, so in the Rouliad, everything is ultimately made of eames. Eames can be interpreted as there are the atoms of existence, and a version of eames is the atoms of space. That is one interpretation of the atoms of existence from the raw Rouliad, is what we experience as the atoms of space from which we build up our notion of physical space. Let's see, I talk about arguments in philosophy, talking about fundamentally different intelligences, and the principle of computational equivalence, talking about equivalence between those, mind-body problem, free will, recognition of other minds. These are all things we've talked about here. Right, and I talk about the idea that somehow logic and mathematics are somehow special as unique foundations of knowledge, and the fact that that isn't true, and the principle of computational equivalence implies that isn't true. Really, I think one of the things that is a sort of a big takeaway from the book is this idea of, the empirical in science and the theoretical in science, and this different idea of the sort of formal empirical or something, this idea of doing computer experiments, studying the Rouliad, studying Rouliology in a way that does not have the empirical aspect of, and then you see what happened based on this physical experiment. Rather, it is an abstract experiment that has a different kind of reproducibility and so on, and a different kind of experiential character than in sort of traditional views of empirical science. All right, so that's kind of everything that I have in the what we could say the data, the content of the NKS book. There's also metadata in the NKS book, and let me show you a little bit of that. So what I've gone through here is the book and what it has to say, leading up to this kind of observation of the computational universe, its implications for specific questions about how the natural world works, to its more global idea of the principle of computational equivalence and the big sort of philosophical implications of that. Now, I also, in writing the book, there was quite a lot of meta information that I gave about the book, and have quite a lot of these notes, which are quite fun. I talk about the website for the book, which is still very much active, and in fact is about, in this next week, will become, get even more material on it, that wolframscience.com. These are notes to the notes, so to speak. These are general notes, and some of them are kind of fun. Talking about, these are notes are sort of separated. I talk about the writing style in the book, and I talk about all kinds of things. Oh my gosh, this is so detailed. I talk about the fact the book wasn't easy to write. Yeah, it took a decade to write, so it was sort of self-evidently not easy to write. But one of the things is it has, I tried to write it in such a way that I could write complex intellectual arguments in plain language, which is not an easy thing to do. And it was plain language plus pictures. And I comment here that probably most annoying, perhaps most annoying to those with a copy editing orientation, would be my predilection for starting sentences with conjunctions. And that was avoiding the philosopher's trap of people like Immanuel Kant, of having sentences that are a whole page long. And so at least we have sort of breathing room, even if a new sentence has to begin with a conjunction. Let's see. This is really advice about reading each paragraph. Readers will pause a moment to absorb each idea before going on to the next one. Oh boy, I comment on the fact that this is a different style of writing than I've used in other places. Really, I made a decision in writing the NKS book that it will be written in first person. I hadn't done that before. And it will be written, but it will be written without whimsy. It will be written without stories. There are many stories I can tell about every page of the NKS book. But it will be written without those stories, but it will be written in first person. And it will be written in a way, I talk about that here, oh boy. There's something probably doesn't even need to be said 20 years later. The word billion means 10 to the 9, not the British use. I talk about another feature of the writing style, which is say what's important. I tell this to people who write things like technical documentation all the time. I say what's important. Don't hide the thing that's really important, and saying, you got to say it is important that, et cetera, et cetera, et cetera, or people don't understand. And people are like saying, it's like, really, what was important about that, so to speak. So, this was a thing that I kind of decided to do in the NKS book. It's kind of putting oneself out there in a sense. It's just say what one thinks is important. Don't say, if one thinks this is a critical idea, say it's a critical idea. People say, oh, no, you can't have a critical idea. You can't say it's a critical idea. It defeats itself by saying it's a critical idea. But no, actually, it's really important to say it's a critical idea, or people just read straight past it. And so that's that. This is a note explaining that point of view. My gosh, this is talking about, I forgot some of these notes. This is about discussing the extent to which you contextualize an idea based on its history. I kind of learned something from Charles Darwin in this respect, that the first edition of Origin of Species often just stated ideas. Subsequent editions often kind of said, well, Professor so-and-so comments on this and that thing, so I'm going to respond to that. Nobody's ever heard of Professor so-and-so now. And the original presentation was just fine. So it's kind of believe in what one believes in and say what one has to say. And there may be context, and the context may in fact be made to be rather irrelevant by what one's figured out. And so don't smother what one has to say in the context. And that's kind of part of the point here, is that I tried to put in the notes a really good historical description of the relationship of ideas for people who know about some of that history or who are curious about that history. But when you explain the raw idea, you don't need to smother it in that history. Oh yeah, this is a fun one. I knew perfectly well as I wrote the book that some technology references would become totally obsolete. And I was just looking actually for, if anybody has examples of these, please send them in because I'd like to know them. I thought I'd mentioned PDAs, personal digital assistants, which were a thing 20 years ago, and not really a thing today. But I was looking for some of these because I wanted to use them as examples. But there are definitely things where I know perfectly well, just like Alan Turing wrote about Brunswigers, which were a brand of mechanical calculator. I know that there are things that I'm writing about technology, which become sort of dated. I talk about whimsy here. There's a certain, particularly at the time I wrote the NKS book, or at least the time I started the NKS book, there are a lot of kind of popular science books and books about kind of popular math and so on, where, you know, if they explained a cellular automaton, they could never just explain it as a bunch of black and white squares. They always had to talk about, imagine people who are holding up black and white cards and somebody's talking to their neighbor and doing this and that and the other. Personally, I can't stand those explanations. They just add, it's like, what's important about this? Where, you know, does it matter that the person can whisper to their neighbor? Does it matter that so that the person two along doesn't hear it? What matters, what doesn't? If you just give it explicitly as a picture, you know what you're talking about, and you can tease out what's important and what's not. Whereas in these kinds of whimsical descriptions, which I avoided in the NKS book, even though they're sort of a thing which some people believe makes it easier for people to understand things. I think it's kind of a wimp out. I think that that's not the point. I think that the ease of, there are things that are really quite hard to understand, and making them whimsical is not going to make them easier. You really, in my experience of explaining things, you know, hitting the nail firmly on the head as quickly as possible and trying to sort of hammer it in, so to speak, directly is a much better strategy than trying to come at it from the side and see what's important and hope that you're going to sort of float down to the end. That's the detailed timeline of writing the book. That's talking about how you can tell what's new in the book, which is an awful lot of stuff, but the history notes kind of indicate what isn't. Oh yeah, this is funny. This is, you know, of course nobody read this, but academics have a habit of, you know, like read from the end, turn to the end of whatever you're looking at and see the list of references, because you can tell a certain amount from the references in something. But turns out I just recently established this. I had about 8,000 papers and 5,000 books that I looked at in connection with the NKS book, and the amount of scholarship necessary to turn those into sort of citations is outrageous. What I did instead was to concentrate on really writing good narrative histories of things, which I think I did rather well at. And those are hard to do. In many ways, they're much harder to digest things to the point of writing a narrative history than it is to just say, reference 1, 2, 3, 4, 5. But I didn't do that. And it's amusing because I said, you know, 20 years ago, I said, look, if you want to know, you know, so long as I have the keywords in the main text or in the notes, you just go to the web and you can find the things. And that's very, very, very true. And you can find them better than you could find them by looking at, you know, it's the physical review, volume, blah, 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 page, blah, blah, blah. Well, I used to, when I was a kid, I used to enjoy going to libraries and things and finding, you know, physical review, whatever, going through a list of references in a paper, and physically, it's probably a good way to get exercise. Physically walking up and down the, you know, the aisles of the library, pulling down the books and sometimes blowing the dust off the top of them to find a particular reference. But I figured that the web would be a way to cover that. Okay, this is explaining historical notes. And yeah, I talk about a bunch of aspects of these historical notes. It's kind of interesting, there's one point, it's looking at the notes, it's striking feature how often individuals of significant fame are mentioned, but not for the reason that they're usually famous. And I think the reason for that is that without the paradigm, without kind of the NKS paradigm, people were figuring out interesting things, but they didn't have a framework to put those into. And so those didn't become sort of the big things that that people discovered. Cans of worms about dates, not doing autobiographical stuff. Okay, this is what the cover image is. This is what the end papers are. This is why I didn't use color in the book. In addition to it being really expensive, it's actually quite misleading for many of the kinds of pictures that I've used, although in more recent times, now that color is so trivial to use, I've found great ways to make use of color, for example, in the physics project. The algorithmic diagrams created for the book, a ridiculous note about hyphenation. I tried to avoid using hyphenation. That often meant, because I was actually laying out the book myself directly in a what you see is what you get kind of environment, I was able to rewrite things or rekern things to avoid hyphenation, which I did. This is talking about the book production system. Actually, I'm just writing a very long piece, which will come out soon, that is specifically about the production of the book. The printing of the book was a very complicated issue that maybe I'll talk about that at a different time. The index was another big adventure. The index is huge. I think it has 15,000 entries in it. It's also kind of interesting to read because it's so bizarre how diverse the index is. Talking about people in the index, I added to the index tagging people by their dates and the primary place where they worked. And so this is a description of what that means, what the primary place means. Okay, this is about the use of notation. This is a summary of a few Wolfram Language features that are used in the book. And this is programs and what's, I haven't looked at this in forever. This is about the programs that are given in the book. This is about acknowledging my computers that I used over the course of my life, getting to the point of this book. It's kind of like a tip of the hat to the computers and all the humans who created those computers. At different times, I primarily used a Next computer, the early years, and then I guess I was using Next Step on an HP, and then I switched to a PC, and then I switched to a Mac. Last 20 years or so. Okay, this is another complicated thing. Maybe I should not go through this. This is about how to present what's in NKS in education. It's a very interesting topic, which I'm afraid has not developed as well as I had hoped it would over the last 20 years. It's still something to develop today. Surprisingly, young children are able to grasp many key ideas in this book. By the time this book was finished, my oldest child was still very young, but I was able to get some good data there. And I talk about the role of mathematics as a core part of education. I kind of view NKS as being kind of a pre-computer science. It's the concepts of computation in a disembodied form, developing intuition, which actually goes beyond the intuition that you get from sort of engineering computer science. I also talk about the fact that what's in the book, the science in the book, makes genuine research accessible to people with almost no specific technical knowledge. And that's another thing which we've seen quite a bit of. And as we develop the field of ruleology, which is kind of the study of systems with simple rules that we're now defining, that I think that ruleology will have a strong amateur component, and we need to understand how to develop that community in the best possible way. This is about kind of how to read the book and which sections to look at. Sometimes when people say, I'm going to read the book, I say, read chapter 1, chapter 2, and chapter 12. That gives you critical pieces. Gosh, this is learning about the science. Big message here is do experiments. That way you'll get intuition about how the science works. Oh boy, this is about, I forgot the length of these notes. This is about kind of developing the community around the science. And I would say there's still a lot more to do here. Some of this has happened, but much has not happened and still remains. And I think it's partly relates to kind of the way that we think about the whole future of basic research. This is about applications and using modeling, and then we are we're wrapped around. Boy, I didn't know the notes wrapped around like that. It's a cyclic thing here. After we get to the very last note, we get back to the beginning again. All right, that leads me to just a couple of last things. I want to show you the colophon to the book. That's the thing that sort of explains the meta story of the book. As I say, I'm writing about this, a very long piece. It's already like 200 pages about the making of the NKS book, which I hope will be out soon. But this kind of gives some, this paragraph, the book was printed on 50-pound Finch VHF paper on a sheet-fed press. It was imaged directly to plates at 2400 dpi, etc. There is a lot to that story, which I'm just writing about now. And this is, there's my 15,000 index entries and so on. And a lot of people, I'm happy to say, many of these people I still work with today. Others have gone on to do all kinds of interesting and different things, people who helped with the book in one way or another. And talking about that, I just want to go back for a second and look for a second at the preface to the book. I think I talked about the main part of this preface before, at the very beginning of my 12-week period, but the preface actually has a giant chunk of small print that is really about the story of, is about sort of the more personal aspects of the creation of the book, and sort of the thanks to all kinds of people and organizations that led to the creation of the book. People, long list of people. I think there are 280 people in this list, of whom 90 are no longer alive. And I think 280 people in this list of people who, in one way or another, contributed to my understanding of things that wound up in the NKS book. And as I say, sometimes there were just a few interactions. Sometimes the main thing that I learned from somebody was what wasn't known in a particular field. But that was a lot of people who I interacted with in learning what I needed to learn for the book. And I think I write at the end, to write the book has taken almost 10 years of continuous work, 100 million keystrokes, more than 100 mouse miles. And I got tens of gigabytes, hundreds of thousands of pages of Mathematica notebooks. And we're steadily making those available online, and making sure that there was sort of a whole nest of particular functions that were created for the purpose of creating the graphics and so on for the book. And we're gradually sort of unpeeling those to the point where there is sort of click-to-copy immediate use code in this. But this is kind of the, in some sense, this this preface represents a very desiccated version of kind of the story of those parts of my life which led to the NKS book. And I could expound on many of those, but won't here. All right, I think that it is, I have to wrap up here very soon. But I see that there were some questions that came in, and I think perhaps let me just comment on a few of these. Sander is commenting about, what about the project of simplifying all the code in the book with current Wolfram Language technology? Yup, we are on it. We are trying to do that. It's been, it's something I kind of enjoy doing it myself, but, I have no time to do that. I think if I was, for some reason, just unable to do anything else, I might spend my time doing things like that. It's really kind of fun. Let's see. Brad asks, is artificial intelligence a UFD? Does that mean unit factorization domain of axiomatic ideas? In other words, it's like a particular property that exists in axiomatic ideas. That is, that the human slice of thinking is a particular feature of sort of the Rule idea. I think that's, in a sense, true. let's see. Let's see, just looking through. Gosh, okay. Well, listen, I think we've probably come to the end here, but thanks for joining me on this journey through the NKS book. I encourage you guys to, you can still get actual NKS books and, get the hardcover version. Don't settle for the soft cover. The hardcover is very lovely, and take its dust jacket off because it's much better without the dust jacket on. And as I've learned recently, don't leave it in the sun if you want was an admonition from the printer saying in 20 to 40 years the red ink will start to fade, and I can tell you that in about a decade in direct sunlight it does. But in any case, there will also be we are going to be releasing a boxed set of both this book and a new collection of things that I've written about NKS, including some new ones, will be coming in a 20 years of a new kind of science, a separate book coming soon, and lots of other interesting things coming for the 20th anniversary, which is coming up at the end of this week. And I am trying to write, among other things, this piece on the making of a new kind of science that really tells some of the story of, including the details of the printing process for the book, which are quite non-trivial, quite a tale of a technological adventure. And I'm trying to get that written by the end of this week, and it's 200 pages long, so lots of work to do, and something I need to go and attend to. But thanks very much for joining this, and I hope you found it interesting, and I hope you'll be motivated to maybe look at what's actually in the NKS book online or in paper, and to, if you're not already doing so, to pursue some of the ideas that are contained there.